Welcome to the third lesson of module 3, which is on thin walled pressure vessels, and we have looked into some aspects of thin walled pressure vessels in the last two modules or two last lessons in fact, and in this particular lesson we are going to look into some more aspects of thin walled pressure vessels. So, this is on thin walled pressure vessels part 3, which is of course the application of stress and strain. Well, it is expected that once one goes through this particular lesson, should be able to understand the concept of volumetric strain in thin walled pressure vessels. Now, in the previous lessons we had looked into some aspects of cylindrical pressure vessels and spherical pressure vessels, that how the strains are generated when it is subjected to internal pressure. Now, because of changes in the strain or because of the change in the deformation, the cylindrical members or the spherical vessels, they undergo change in the volume. So, we will like to evaluate that what is the strain in terms of the volume. So, change in volume over the original volume, which we call as the volumetric strain. Now, what is the value of those for different pressure vessels? Also, one should be able to evaluate stresses and deformation in thin walled pressure vessels and appreciate the difficulties. Now, we will look into some aspects, especially when we discuss about the combination of spherical and cylindrical vessels, that what are the problems related to the deformation and what are the aspects should be looked into when one should go for the detailed analysis or design of such vessels. Hence, the scope of this particular lesson includes the recapitulation of previous lesson, which we do generally through the question answer session. We will look into the answers of the questions which I have posed last time, and thereby we will be able to recapitulate the aspects which we have discussed in the last lesson. And then we will be deriving the formulae for evaluating volumetric strain in thin walled pressure vessels, both cylindrical type and spherical type. And then we will be looking into some examples for evaluation of stresses, strains and deformations in thin walled pressure vessels, and these examples also will be related to cylindrical type of pressure vessels or spherical type of pressure vessels. Well, let us look into the questions which I had posed last time, and the first question was, what is the value of maximum strain in spherical vessels? Now, in the last lesson we had discussed aspects of the spherical vessels, that if a spherical vessel is subjected to internal pressure, then how the deformation takes place, and consequently what are the stresses and strain that occurs in the spherical vessel. So, now let us look into what is the value of the maximum strain. Now, we had evaluated the values of the stresses, and if you remember, for a spherical system or a spherical vessel of this kind, the stress that exists is the sigma, both in the x and the y direction, and we had written down the resistive force, which is sigma times area, which is equals to twice pi r t, where r is the radius of the internal radius of the sphere or spherical vessel, and t is the thickness, of this particular vessel, and the pressure that is being exerted by the content inside the container, this is capital P, which is equals to the pressure P times pi r square, and these two when we equate, we get the value of the stress. So, this gives us the value of sigma as equals to P r by 2 t, which we have evaluated last time. Now, this is the amount of stress. Now, this is being a spherical vessel. Now, wherever we take a section through the center, we get identical type of stresses, and hence the on this particular element we have both in the x direction and y direction the value of normal stress as sigma. Now, if we like to compute the strain, let us say based on this stress, if we like to compute the strain, now strain, as we know, if we want to compute in the x direction, is equals to sigma x by E minus mu times sigma y by E. Now, here since sigma x and sigma y both are sigma, sigma x is equals to sigma y is equals to sigma. Hence, if we substitute over here, we get epsilon x as equals to sigma by E minus mu sigma by E, and this is equals to 1 minus mu divided by E times sigma. So, corresponding to the maximum value of the stress, which is equals to P r by 2 t, we can compute the strain, and the strain, let us call this as epsilon, which is as a function of stress sigma. So, this is the maximum strain that occurs in a spherical vessel. Now, the second question posed was, what is the value of in plane shear stress in spherical vessels? Now, if you remember, last time we had discussed the in plane stress in a cylindrical pressure vessel, wherein we said that if you have the values of sigma x and sigma y as sigma 1 and sigma 2, sigma 1 was the circumferential stress and sigma 2 is the longitudinal stress. So, if we take these two stresses and compute the we can compute the strain, and also in terms of these stresses we can compute the in plane shear stress. Now, sigma 1 for cylindrical pressure vessel was P r by T, and sigma 2 was P r by twice T, and as we have seen in case of spherical vessel, sigma is equals to P r by twice T, and here both the values of sigma 1 and sigma 2, which was in the longitudinal direction in case of cylindrical member. In case of spherical vessel, they are the same, and this is P r by twice T. Now, as we had seen in case of cylindrical vessel, that the shear stress is sigma 1 minus sigma 2 by 2 is the maximum in plane shear stress. This is maximum in plane shear stress, and this is equals to sigma 1 minus sigma 2 by 2. Now, in this particular case, since both sigma 1 and sigma 2 are the same, or sigma x sigma y is sigma, hence the value of the in plane shear stress in case of spherical vessel is 0. So, in plane shear stress in case of spherical vessel is equals to 0. Now, third question was, are the stresses same in spherical vessels as observed in cylindrical vessels? Now, this was the question which was posed in the previous lesson as well. Now, what you need to look into the derivations as we have done for both cylindrical vessels as well as the spherical vessels, and if we look into, we can immediately get an answer for what is the difference between the two. Now, in case of cylindrical vessels, if you remember that we have circumferential stress which is sigma 1 and sigma 1 times T times L for the length L of this element. This was equals to P times twice R times L, and from which we had calculated that this L gets cancelled. So, sigma is equals to, this is twice of this because you have this as well as this. So, this 2 also gets cancelled, is equals to P r by T, and consequently the longitudinal stress sigma 2 we had obtained as P r by twice T. Now, in case of spherical vessel, as we have seen right now, that we have only one stress which is equals to sigma, and that is equals to P r by twice T. Now, please note that in case of cylindrical vessel, we have the circumferential stress which we have called as hoop stress as well. This is circumferential stress or the hoop stress, which is equals to P r by T, and the longitudinal stress is P r by 2 T, which is half of this sigma. So, sigma 2, as we have seen in the last time, is equals to sigma 1 by 2, and the stress which we have in case of spherical vessel is equals to P r by twice T, which is again half of sigma. So, this is sigma 1 by 2. So, in case of the maximum normal stress which we get in case of cylindrical vessel, maximum normal stress is equals to sigma 1 which is P r by T, and maximum normal stress, this is for the cylindrical vessel, and for spherical we get maximum normal stress which is equals to P r by 2 T. So, it is half of that. The maximum normal stress in case of spherical vessel is half of that of cylindrical vessel. Now, this aspect probably you can appreciate more through this particular diagram. Now, if we look into, say, this is the stress corresponding, this is the sigma 2 which is the longitudinal stress, this is an element which has been taken out from cylindrical vessel. Now, in case of cylindrical vessel, what happens is along the longitudinal axis, the stress which exists really does not contribute to the equilibrium of the pressure which is being exerted on the curved surface by the content of the liquid or the liquid. Now, only the stresses that resist the internal pressure is the circumferential stress, and hence the value is larger, whereas in case of spherical vessel, as it can be observed from this particular figure, here we get the stress from both directions. That means, the stress which is being exerted or the pressure which is being exerted by the content of the spherical vessel is being resisted by the vessel in all directions. Now, as we have seen in both the cases, both for cylindrical as well as the spherical vessel, the pressure which is exerted on the curved surface, they are the normal to the surface, and since the wall is thin, the variation of the stress across is negligibly small, and we disregard that, and hence we have a biaxial state of stress which is in terms of sigma 1 and sigma 2. Now, in case of cylindrical pressure vessel, this longitudinal stress does not really contribute much to the equilibrium of the curved surface, whereas in case of spherical vessels, the curved surface or the stresses from both directions comes in the resistance of the pressure which is being exerted by the content, and that is the reason the stress in case of cylindrical one is more than the spherical one, and in case of spherical vessel we have uniform tensile stress over the entire surface, which we normally call as the membrane stresses. Also, if we look into this particular aspects of it, this is to be noted that if we have a vessel which is a combination of cylindrical vessel and this is the cylindrical part, and the two ends we have the hemispherical part. So, this is spherical part, and this end as well we have the spherical part. Now, this is a combination of cylindrical and spherical vessel. Now, as we have seen that the stress in case of cylindrical one, which is P r by T, is larger than the stress corresponding to the spherical vessel, which is sigma, which is P r by twice T. And also, if we compute the deformation, we will find that the deformation in case of cylindrical one, which is given by this, let us call this as delta, is also larger than the deformation which is caused in the spherical part, if we call this as delta 1. Now, the problem arises at this particular junction, where the container is a combination of the end of the cylindrical part and the starting of the spherical part. Now, at this particular junction, as we can see that we have larger deformation from the cylindrical end, we have smaller deformation from the spherical end. So, as a result, there is a mismatch in the deformation at that particular junction. Now, so far as the whole assembly is concerned, now there should be continuity of the element, and thereby there will be some other kind of stresses will be generated apart from the stresses that we are discussing over here. So, when we go for the design of such system, when we try to go for sizing of such system, one should be careful in selecting the sizes, and one should be concentrating on the type of stresses that gets induced at that particular junction, and accordingly the thickness has to be decided. Now, at this point of time we are not going into the detail of that, only I am just trying to highlight the problem that can arise in case of such pressure vessels, where you have the combinations of cylindrical and the spherical one. But for the time being we assume that geometrically there will be smoothness and we will have similar kind of pressure exist, and the corresponding deformation we can evaluate directly without considering the change in other kinds of stresses. Well, now having looked into this, now as I said that when you have liquid inside the container, whether it is a cylindrical vessel or spherical vessel, now as we have seen through the examples in the last two lessons, that it undergoes change in the diameter, thereby it undergoes change in the volume of the container. Now, if a volume of cylindrical or spherical vessels undergoes changes, then we should be in a position to compute that what are the changes in the volume. Now, as we have defined strain in case of a linear element, that extension to the original length is the strain, the ratio of the extension or the deformation to the original length is the deformation. Now, in case of volume change, we define that the change in the volume to the original volume as the volumetric strain. Now, we will be looking into that what will be the how we are going to evaluate the volumetric strain in case of cylindrical or spherical vessels. Now, let us look into the evaluation of volumetric strain for cylindrical vessels. Now, the value of the volumetric strain E, which last time if you remember we had defined delta V by V when we had computed the value of the bulk modulus, and we had designated that as E. We can evaluate this volumetric strain as a function of the pressure, the radius of the vessel and thickness of the vessel, and correspondingly the values of materials which are E and mu. Now, let us look into the evaluation of this volumetric strain. Now, if we consider a cylinder, having length L and radius R, let us say the internal radius is equals to R and length is L. Now, after deformation, let us say the change is R plus delta R in the radius and L plus, consequently L plus delta L is the change in the length after the content has exerted pressure and the dimensions have undergone changes in terms of the deformation. Now, if these are the changes, then the volume of the cylinder delta V by V is equals to, this is pi R plus delta R square times L plus delta L, this is the change volume, minus pi R square L is the original volume divided by pi R square L. So, this is the final volume after the deformation has occurred minus the initial volume divided by the initial volume. So, this is E, which is del V by V. So, this is equals to, if you take out pi from here, we have if we expand this R plus delta R square, this is R square plus delta R square plus twice R times delta R. This is multiplied with L plus delta L minus R square L divided by pi R square L. So, pi pi gets cancelled. So, this is equals to 1 by R square L times, if I multiply with L, this is R square L plus L delta R plus twice R L delta R plus R square delta L plus delta L delta R plus twice R delta L minus R square L. So, this R square L gets cancelled, and if we neglect delta R being small, if we neglect the multiplication of delta R times delta L, this kind of values. So, this is equals to 1 by R square L times, we have twice R L delta R plus we have R square delta L. Now, this also this quantity we neglect, and this is delta R square. So, L delta R square, this is square. So, this term also we neglect, this being delta R being small, square of that will be very small, and also delta R delta L being smaller, the product of delta R and delta L also we neglect. So, we are left with these two terms, and this is equals to, if we divide by R square L, this becomes twice delta R by R plus delta L over L. Now, as you can realize that delta R by R is nothing but the strain in the radial direction, which we have called as epsilon 1, or sigma 1 is the stress in the circumferential direction for cylindrical vessel, and delta L by L, which is in the longitudinal direction, the change in length over the original length, which is the strain in the longitudinal direction. So, this is equals to, you can write as twice epsilon 1 plus epsilon 2, and mind that epsilon 1 is the strain in the circumferential direction and epsilon 2 is the strain in the longitudinal direction. So, the volumetric strain E is equals to twice epsilon 1 plus epsilon 2. Now, this if we write down in terms of the stresses, we have obtained E as equals to twice epsilon 1 plus epsilon 2, and epsilon 1 if we write in terms of stresses as sigma 1 by E minus mu sigma 2 by E, plus epsilon 2 is sigma 2 by E minus mu sigma 1 by E. And also, as we know, sigma 1 is equals to P r by T and sigma 2 is P r by 2 T. So, we write this as P r by T times E minus mu P r by 2 T E plus P r by 2 T E minus mu times P r by T times E. So, this is equals to, then if we take out P r by T twice P r by T E, this gives 1 minus mu by 2, plus from here if we take out P r by T E, we have half minus mu. So, from here if we take out P r by T E out for the whole, we have 2 minus mu, this is 2 gets multiplied, plus 1 minus twice mu by 2. So, this is equals to P r by T E times 2 to 4 plus 1 5. So, 5 minus 2 to 4, 4 mu by 2, and this is what is the expression which we have obtained as P r by T E times 5 minus 4 mu by 2, or P r by twice T E 5 minus 4 mu, and this is the expression which we have obtained, and this is what we have written, that delta V by V is equals to P r by twice T into 5 minus 4 mu. This is the volumetric strain in case of cylindrical pressure vessel. Now, likewise we can compute the volumetric strain for spherical vessel as well. Now, in case of spherical vessel, the volumetric strain in case of spherical pressure vessel is given by E equals to delta V by V, again as 3 P r into 1 minus mu by twice E, and we can compute the value exactly in the same way as we just now did. Now, supposing if we have a spherical vessel for which internal radius is again as r, and because of internal pressure there is a change in the radius which is r plus delta r, this is the changed radius. Hence, the value of the volumetric strain which is E, which is equals to delta V by V, is equals to delta V is the final volume minus the original volume, which is 4/3 pi times r plus delta r cube minus 4/3 pi r cube. this is delta V divided by the original volume, which is 4/3 pi r cube. So, this is equals to, if you take 4/3 pi out, then we have r plus delta r cube minus r cube divided by 4/3 pi r cube, this gets cancelled. So, this is equals to 1 by r cube times, this is r cube, it is 3 r square delta r plus 3 r delta r square plus delta r cube minus r cube. So, this gets cancelled. Now, again with the same logic that delta r being small, so we neglect the value of delta r square and delta r cube. So, we are left with 3 r square delta r, which is equals to 3 r square delta r divided by r cube, and this gives us 3 delta r by r. And again, as you can see, delta r by r is the radial strain. That means, delta r is the elongation in the radial direction, and that divided by the original radius will give you the strain. So, this is nothing but equals to 3 times epsilon. So, E, the volumetric strain, is equals to 3 times the normal strain. Now, we can compute the value of E in terms of stresses, and that if we do, it comes as, say, E, as we have seen now, is equals to 3 times epsilon, and epsilon we can write in terms of sigma, which is equals to 3 times 1 minus mu by E times sigma, and sigma, as in case of spherical vessels we have seen, as equals to P r by twice T. So, this is nothing but equals to 3 into 1 minus mu by E into P r by twice T. So, this is equals to 3 P r by twice T E into 1 minus mu. So, this is the value of the volumetric strain in terms of the internal pressure, the radius, and the thickness, modulus of elasticity, and the Poisson's ratio. So, this is what is represented here, that the value of the volumetric strain E is equals to 3 P r times 1 minus mu by twice T E. So, now that we have looked into that what is the value of volumetric strain for a cylindrical vessel and for the spherical vessel. Now, as you can look into that, we have discussed the small difficulties which we encounter when we go for a combination of a spherical and cylindrical vessels at the junction, where there is a mismatch in the deformation, and to make the geometrical compatibility, or if we have to have a smooth deformation over there, then thereby there will be additional stresses which has to be taken into account when you go for the design of such vessels. Well, then after discussing this, let us look into the examples that are related to these cylindrical and the spherical vessels. Now, the first of such example is that a spherical stainless steel tank having a diameter of 400 millimeter, is used to store propane gas at a pressure of 2.4 megapascal. Now, the yield stress of steel in tension is 112 megapascal, value of E is given as 200 GPa, and the Poisson's ratio as 0.28. Also, the normal strain, it is stated that the normal strain in the vessel should not exceed 1000 into 10 to the power minus 6. So, under these constraints, we will have to determine the minimum permissible thickness of the tank. So, a spherical tank is used for storing gas. Now, certain parameters are given, the diameter is given, the thickness is given, thickness is not given, we will have to find out the thickness of the tank. If you have to contain this gas, subjected to that, the pressure is subjected to a maximum stress of limit given and the maximum strain limit given. So, from these two criteria, you will have to evaluate the value of the thickness. Now, let us look into that, how do we compute the value of the thickness. Now, the diameter of the tank given is 400 millimeter, the pressure inside is equals to 2.4 MPa. The stress limitation, the maximum tensile stress that can be applied on the vessel is equals to 112 MPa. The value of E given is 200 GPa, the gigapascal. Mu is given as 0.28, and also it is stated that the strain limitation, which is 1000 into 10 to the power minus 6. Now, if we try to compute the stress, now since there is a limitation on the stress as well as on the strain, so we have to compute the thickness of the vessel from two considerations. First, we compute that what is the maximum stress that can be generated because of the pressure exerted by the content, and from there we will get one thickness. Also, when the vessel is subjected to internal pressure, there will be strain on the surface, and there is a limitation on the strain value as well, and corresponding to that strain we will get another thickness. Now, we will have to go for the thickness which will satisfy both the criteria. So, let us look into first with reference to stress. So, maximum stress that can be generated in a spherical vessel, which is sigma, is equals to P r by 2 T. This we have seen, and here P is given as 2.4 MPa megapascal. So, 2.4 times diameter given is 400. So, radius is 200 divided by 2 times T. So, T is the thickness which we will have to evaluate, and mind that this particular stress is limited to 112 MPa. So, this is equals to 112 MPa. Now, from this particular consideration, from this equation we can compute the value of T, and if we compute the value of T, T from this equation comes as 2.143 millimeter. So, this is the value of T is required to satisfy the stress requirement, or the maximum stress that should not be exceeded is 112. So, to satisfy that criteria, the thickness which we need is this. Now, for the strain requirement, as we know, epsilon is equals to epsilon x. If we talk about it, is sigma x by E minus mu sigma x by sigma y by E. Now, in this particular case of spherical vessel, sigma x and sigma y, they are same and they are sigma. So, this is equals to 1 minus mu by E times sigma. So, that is the value of strain epsilon. Now, here the value of the Poisson's ratio mu is given as 0.28, this divided by E, which is 200 times 10 to the power 3 megapascal times sigma. Now, sigma we write as a function of T, which is 2.4 into 200 divided by 2 T, and this strain, as it is given, that cannot exceed a value of 1000 into 10 to the power minus 6. So, this is nothing but 10 to the power minus 3. So, 10 to the power minus 3 is the limiting value of the strain, and that is written as a function of T through this expression, which is equals to 0.72, and this 200 gets cancelled, times 2.4 divided by 2 into 10 to the power 3 into T, and this is equals to 10 to the power minus 3. So, from this, if we compute the value of T, T comes out to be as 0.864 millimeter. T is equals to 0.864 millimeter. Now, as we can see that we have two values of thicknesses as we have obtained. One is corresponding to the verification of the maximum strain value, other one is corresponding to the satisfaction of the stress criteria. So, if we have to satisfy both, now if we go for a lower thickness, then there is a possibility that the stress level here will be higher, and as a result it will not satisfy this criteria. But if we go for a higher thickness, then it will satisfy the strain criteria. So, the thickness which is to be adopted is equals to this, T is equals to 2.143 millimeter. So, this is the thickness of the vessel that is to be adopted, so that it satisfies both the criteria of stress as well as the strain. The maximum value of the stress requirement, which is 112 MPa, and the maximum value of the strain requirement, which is 10 to the power minus 3 is the value. So, these two can be satisfied if we use a thickness of higher of the two thicknesses, which is 2.143 millimeter. Well, now let us look into another example problem, wherein we have a circular cylindrical tank, we have circular cylindrical steel tank which contains a volatile fuel under pressure. Now, a strain gauge at A, now there is a, at this particular location a strain gauge is fixed. Now, that records the longitudinal strain in the tank. Now, here you see that we have a cylindrical tank, this part is the cylindrical part, and on this there is a hemispherical ends attached to the tank, and this contains a volatile fuel inside it which exerts pressure. Now, on this cylindrical surface there is a strain gauge mounted. Now, this strain gauge sends the information, that it transmits the information to a control room about the strain on such vessels. Now, it is indicated that the ultimate shear stress in the wall of the tank is 41 MPa. Now, what you will have to find out is that the operator who is operating this particular system, now at what strain, now since he is recording at the control room, he is getting the constant record of the strain. Now, at what strain he should reduce the pressure, so that the stresses in the vessel does not go beyond its limiting capacity. So, that is what is being controlled. In the vessel we have fixed a strain gauge, and the strain gauge data is being transmitted to the control room. Now, the content is giving a pressure inside, and because of that the strain is changing, thereby the stresses are changing. Now, there is a limiting value beyond which there is a possibility the whole thing may burst. Now, so the operator who is controlling that, he has to keep an eye, so that the strain value, if it goes beyond a particular value, it is under risk and the pressure has to be reduced inside the container. So, we will have to compute that value of the strain for which the operator should reduce the pressure, and the value of E is given and the value of the Poisson's ratio is given over here. Now, let us look into then how do we compute the value of the strain at which the operator should send the signal that it is to be stopped or the pressure is to be reduced. Now, the value of E is given as 205 GPa gigapascal, and the value of mu is equals to 0.3, the Poisson's ratio. Now, as we know that in case of spherical vessel or in case of cylindrical vessel, the value of sigma 1 and sigma 2 can be computed in terms of the pressure, and we have, if we take a small element, we have sigma 2 in the longitudinal direction and sigma 1 in the circumferential direction. And as we have seen that the shear stress, in plane shear stress tau is equals to sigma 1 minus sigma 2 by 2. Now, it is indicated here that the maximum shear stress is equals to 41 MPa. So, the value of the stress differential sigma 1 minus sigma 2, this is equals to 82 MPa. Now, also we know that in case of cylindrical vessel, sigma 1 in terms of pressure can be computed as PR by T, where P is the internal pressure, R is the radius, internal radius, and T is the thickness. And in case of longitudinal stress sigma 2, this is equals to PR by twice T. So, this longitudinal pressure sigma 2 is equals to sigma 1 by 2. Now, if we adopt this value over here, we can write this as sigma 1 minus sigma 1 by 2, this is equals to 82 MPa. So, sigma 1 is equals to 164 MPa. So, this is the value of the circumferential stress, and thereby the longitudinal stress is half of that, which is 82 MPa. Now, if we know the stress, then the strain, now that we have a strain gauge which is fixed in the longitudinal direction of the vessel. On the cylinder, on the cylindrical vessel we have fixed one strain gauge which is in the longitudinal direction. Now, which will record the strain in the normal longitudinal direction. So, we will have to compute the value of the strain in terms of the stresses. So, the strain in the longitudinal direction which we are calling as epsilon 2 in line with the stress sigma 2, epsilon 2 is equals to sigma 2 by E minus mu sigma 1 by E. Now, sigma 2 as we have seen is equals to sigma 1 by 2, since we are writing everything in terms of sigma 1 by 2. So, this is sigma 1 by 2 E minus mu sigma 1 by E. So, this is equals to sigma 1 by E into half minus mu. Now, mu is given as 0.3. So, this is 0.5 minus 0.3 and sigma 1 is given as 164. So, this is 164 divided by 205 into 10 to the power 3. So, this many megapascal, this was 205 gigapascal. So, 205 into 10 to the power 3, so much of megapascal, this times 0.5 minus 0.3. So, this gives you the value of the strain which comes as 0.16 into 10 to the power minus 3. So, this is 160 into 10 to the power minus 6. So, this is the amount of strain, this is the limiting strain. So, as soon as the operator records that the strain is going closer to 160 into 10 to the power minus 6, the operator should reduce the pressure from the cylindrical tank, so that the stress level does not go to the limiting value of that particular material with which the vessel has been fabricated. So, this is the this particular information is necessary, that is to be kept with the operator, that if the strain value as it is recorded under the pressure, that particular strain as it goes to 160 into 10 to the power minus 6 or is little below that, the pressure inside the vessel has to be reduced, so that the stress level does not go to the criticality. Well, let us look into the third example, which is quite simple a problem, I guess, that cylindrical water tank, a cylindrical water tank has 6 meter diameter. Well, let us take this as our internal diameter only, which is 6 meter, as 6000 millimeter, and the thickness of the tank wall is 10 millimeter. Now, if the working tensile stress is 48 MPa, if the limiting stress on the vessel is 48 MPa, find the maximum height h to which the tank may be filled. Use gamma of water, unit weight of water as 1000 kg per meter cube. Now, this particular tank is filled up with the water. Now, this height h is to be determined up to which, if we fill it up, the stress, the maximum stress that can be allowed to go in the tank is up to 48 MPa. So, this height has to be evaluated from this particular criteria of the stress. Now, let us look into how do we get the value of h if we limit our stress to 48 MPa. Now, here the values which are given, the diameter of the tank as 6 meter, which is 6000 millimeter. Now, the value of T, the thickness of the wall is 10 millimeter. Now, the limiting stress, the working stress of the wall or of the vessel is equals to 48 MPa. So, this is the limiting value sigma, let us call this as sigma working stress that is limited in the tank is 48 MPa, and the unit weight of water gamma is 1000 kg per meter cube. Now, in that particular tank, as the water level is going up, there will be change in the pressure which will be exerted by the water. So, this is the tank. Now, as the water level is going up, say up to level h. Now, the pressure which will be exerted by the water the maximum pressure is equals to gamma W times H is the maximum pressure. So, we got to compute the value of the stress with reference to this maximum pressure, so that the maximum stress can be evaluated in the tank, and corresponding to that we can find out the height. So, because corresponding to the maximum pressure, the maximum stress will be generated, and of course, as the pressure will be reduced, naturally the stresses at different point will be different. Now, for gamma given as 1000 kg per meter cube, so 1000 times H is so much of kg per meter square is the pressure that is being exerted by the water on the tank. Now, if we write in terms of Newton, approximately taking 10, this is 10,000 H Newton per meter square. So, this is the equals to pressure P in this particular example. So, if we calculate now the stress, now this particular cylindrical vessel, the maximum stress, maximum normal stress for cylindrical vessel, this particular vessel is a cylindrical type. So, maximum normal stress, this is equals to sigma 1, which is the circumferential stress, which is equals to P r by T, and this in this particular case as 10,000 times H is the value of P, and R diameter of the tank is given as 6000. So, times 3000 is the radius divided by thickness T, which is equals to 10. Now, this is the magnitude of the stress, and that is limited to maximum normal stress is limited to 48 MPa, because it cannot go beyond that, then the member will fail or the tank will fail. So, corresponding to this, H is equals to, now here this is Newton per meter square. So, meter, and this is millimeter, this is also millimeter. So, if we convert that meter square into millimeter square, so this is 10 to the power 6. So, this gives us, this is 10 to the power 4, 10 to the power 3, 10 to the power 7. So, this is equals to 3 times H into 10 to the power 7 divided by 10 to the power 7. So, this gets cancelled. So, H gives us as 48 by 3, which is equals to 16 meters, because H was in meter as we assumed over here. So, height of the water, if it goes up at the level of 16 meter, then it can go the pressure level up to 48 MPa. So, we will have to if we like to keep the pressure in the tank wall up to 48 MPa, then the maximum height up to which we can pour water is 16 meter. Well, let us look into another problem, which is quite interesting. Now, here you see this is the kind of examples I was trying to explain, that we have a pressure vessel in which is basically a cylindrical pressure vessel, which is this is the cylindrical part having 600 millimeter in length, and is connected with the hemispherical end. The two ends are hemispherical, having a diameter of 400 millimeter, and the diameter of this particular hemispherical end is the external diameter. So, the cylindrical pressure vessel with hemispherical end caps is made of steel. The vessel has uniform thickness of 20 millimeter and the outer diameter of 400 millimeter. Now, when the vessel is pressurized to 4.5 megapascal, now determine the change in the overall length of the vessel. Now, this is the length of the vessel originally. Now, we will have to compute that because of this pressure 4.5 MPa which is exerted on the vessel, then how much increase in the length occurs because of this internal pressure. So, this is what is to be computed that determine the change in the overall length of the vessel. The value of E is given as 200 GPa and mu is 0.3. Now, let us look into the evaluation of this particular values, that how much is the elongation or change in the length. Now, the diameter, outer diameter of the vessel d outer is equals to 400 millimeter, and thickness is 20 millimeter. P is given here as 4.5 MPa and the value of E is equals to 200 gigapascal, mu is given as 0.3. Now, here then the inner outer diameter is given as 400 millimeter. So, the radius outer R outer is equals to 200 millimeter, and since we are dealing with the radius which are inner radius. So, R inner this is equals to 180 millimeter, which is this minus the thickness. Now, if we compute the values of the stresses, now first let us look into the cylindrical part and then subsequently we will go to the spherical part. For the cylindrical part, the change in the length will be the elongation in the longitudinal direction. So, we got to compute the strain in the longitudinal direction and then corresponding what is the change, and then we will look into the hemispherical length and what is the change in the radius. Now, for the cylindrical one, if we look into the value of sigma 1 is equals to PR by T, which is equals to 4.5 into R is 180 divided by T is 20. This gives us a value of 40.5 MPa. Now, value of sigma 2, which is half of sigma, is equals to thereby 20.25 MPa, and correspondingly the strain in the longitudinal direction, which is epsilon 2, is equals to sigma 2 by E minus mu sigma 1 by E, and this gives us a value of, if we substitute the value of sigma 2, sigma 1, E and mu, this comes as a value of 0.0405 into 10 to the power minus 3. So, this is the value of the strain in the longitudinal direction. Now, the strain in the longitudinal direction in terms of the deformation, if delta L is the deformation in the length to the original length, is the strain epsilon, and this is equals to 0.0405 into 10 to the power minus 3. So, change in the length delta L is equals to the original length times this, which is 600 multiplied by this, and this comes as 0.0243. So, this if it is multiplied with the 600 gives a value of 0.243 millimeter. So, this is the change in the length in the longitudinal direction for the cylindrical part. Now, let us look into what is the change in the two hemispherical end, or what is the change in the radius, and that will give us the total change. Now, in the hemispherical end we have sigma as equals to PR by 2T, which we have computed as 20.25 MPa, and correspondingly epsilon is equals to 1 minus mu by E times sigma, which is 0.0708 into 10 to the power minus 3. So, this is the strain. So, strain is equals to change in the radius by original radius, and this gives us a value of 0.0708 into 10 to the power minus 3. So, delta R, the change in radius, is equals to this times the original radius, which is 180 millimeter, and since we have two hemispherical ends, so twice of this value, and this comes as equals to 0.0255 millimeter. Hence, the total change in length is equals to the change in length is equals to delta L plus delta R, and this is equals to 0.0498 millimeter. So, this is the total length in the change as we get in the in this particular vessel. Well, we have another example which I set for you, and we will discuss in the next lesson, which is a thin walled cylinder 4.5 meter long, 500 millimeter internal diameter and 5 millimeter wall thickness is prevented from axial displacement. Now, here the cylinder is not allowed to move in the axial direction. So, it is restrained, and thereby there is a change in the volume, and this is corresponding to the volumetric strain. So, determine the maximum tensile stress and the increase in the internal volume. You got to compute the volumetric strain and thereby the change in the internal volume for this particular pressure. Well, now to summarize what we have discussed in this particular lesson is that we have looked into the concept of volumetric strain in thin walled pressure vessels. So, in this particular lesson we have looked into for cylindrical or spherical vessels how the volumetric strain occurs or change in volume occurs. Then we have observed on some aspects on the deformation when especially the cylindrical and spherical vessels are combined together, then what are the problems we do encounter. And then we have looked into some examples where we could compute the values of strains and thereby the stresses and the deformations in the vessels. And also of course, we have assigned one problem which is related to the change in the volumetric strain. Now, with this particular lesson, in fact, we come to the conclusion of this particular module. In this particular module we had 3 lessons. Now, this particular module is on thin walled pressure vessels and it consisted of 3 lessons. And in the first lesson we had introduced the concept of what is meant by thin walled pressure vessels, what are the kind of stresses that it gets induced, and we had discussed that aspect with reference to the cylindrical pressure vessel. Consequently, in the second lesson we had discussed again with reference to thin walled pressure vessels, but with a specific reference to the spherical vessel, that what are the kinds of stresses and strain occurs and thereby what are the deformations in spherical pressure vessel. And finally, in today's lesson we have discussed the volumetric strain with reference to the cylindrical and spherical vessels and thereby some critical observations on such kind of pressure vessels and how to take care of that, and that we have discussed through several examples related to both cylindrical and spherical vessels or the combinations of that. Now, well, some questions are set for you. Is that first question is, how will you define a thin walled pressure vessel, which is quite clear now. Now, from these lessons you can find out that what will be the definition for a thin walled pressure vessel, what is the nature of stresses in thin walled pressure vessels. Now, what is the relation between the volumetric strain and maximum strain in spherical vessels. So, all these questions in fact you can answer from the lessons which we have discussed corresponding to this particular module, and I am sure that you will be able to get the answers readily from these lessons itself. Well, thank you very much for your attention. Welcome to the first lesson of module 4, which is on torsion part 1. In fact, if you remember that we had discussed in the last 3 modules which are on aspects of stress, strain and application of stress and strain on thin walled pressure vessels. Now, if a bar is subjected to an axial pull, it is subjected to a normal stress which we have seen as load divided by the cross sectional area. Consequently, we have seen that if the bar is subjected to axial pull, it undergoes deformation, which we have defined in terms of strain, the deformation to its original length. Now, in this particular lesson we are going to look into that if this particular bar is subjected to another kind of forces which we term as a twisting moment or torsion, then what are the effect of torsion on such bars. So, it is expected that once this particular lesson is completed or once someone goes through this particular lesson,